So far we have considered resistance and capacitance for wires, but we have never talked about inductance. So why? Because normally inductance is small in interconnects on ASICs, but there are cases, especially in modern technologies, where you have to consider the effect of inductance. So inductance is taken into consideration under two circumstances: when the frequency of operation is high and or when the length of the wire is really long. So inductance generally increases when the area of the wire is big, which happens when the length of the wire is really long. This is always the case, by the way, for off-chip communication, where you are talking about the copper tracks on a PCB. In that case, you have to take inductance into consideration. But we will see that it's also true for some on-chip wires as well. So when you have inductance playing a role as well as capacitance, your wire becomes a transmission line. And so you have to deal with the wire as a transmission line. Here we are talking about an interconnect between chips, which means it's an off-chip PCB track. And when you consider a piece of wire to be a transmission line, you're looking at the signal going through it as a wave. So it's propagating as an electromagnetic wave. And in transmission lines, delay is more controlled or more dominated by the time of flight of the signal, meaning the time it takes the signal to actually, the electromagnetic wave, to actually travel through the length of the wire, rather than by gate delay, which is calculated as an RC delay. So, for example, let's consider the situation where we have a wire with a length of 20 centimeters. This is not huge. I mean, it's kind of long, but it's possible on a PCB. Now, the relative permittivity of the insulator is 4, and the relative permeability of copper is 1. So epsilon r is equal to 4, and mu r is equal to 1. The 4 refers to the insulator from which we make the body of the PCB, and the 1 is the material from which we make the PCB tracks, which is copper. Now, the velocity of the electromagnetic wave traveling through this transmission line is 1 over square root LC, where L is the impedance, is the inductance per unit length, and C is the capacitance per unit length, which is also equal to 1 over square root mu epsilon, the permittivity and permeability of the materials, which can also be obtained in terms of absolute or vacuum level permeability and permittivity, as well as relative permeability and permittivity. So 1 over square root mu naught epsilon naught is C naught, which is the velocity of electromagnetic waves, the velocity of light in vacuum, and this is divided by the permeability and permittivity of the materials. So we can calculate the velocity at which the wave travels through this 20 centimeters long wire, and we can calculate the time of flight of the wave through this wire as the length of the wire divided by the velocity at which it is traveling. So using the values I gave here, you can calculate a time of flight which is equal to approximately 1.33 nanoseconds. Now that means that it takes the wave 1.33 nanoseconds just to traverse the transmission line. Now, if this time of flight is comparable to TPD, or the gate delay within the chips, then you have to take it into consideration. And 1.33 nanoseconds is actually very comparable to most gate delays in modern technologies. So you start to see that with higher frequency of operation, when gates start to become faster and faster, transmission gate effects have to be taken into, transition line effects have to be taken into consideration. But This is also true for longer wires, and we are talking about a 20 centimeters wire here. But even if we're talking about the 2 centimeters wire, we would still have to take this into consideration because the time of flight is still within the order of magnitude of gate delays for most modern gates. Even 2 orders of magnitude lower, we still have to take it into consideration. So even for a 2 centimeters or even a 1 centimeter wire, you still have to take transmission line effects into consideration. And since many chips are actually more than 1 or 2 centimeters as far as the dimension of one side is in modern chips, that means that some on-chip wires, especially global wires that connect distant areas of the chip, will actually suffer from these electromagnetic effects. The problem with transmission line effects is not just that the time of flight becomes significant, is that there is a chance that we will see reflections both at the transmitter and at the receiver. These reflections will change the total delay that we see potentially to many multiples of the time of flight. So a transmission line is characterized by something called the characteristic impedance, Z0, and Z0, or the characteristic impedance, is a small value normally. We're talking about something in the order of 50 ohm. And it's important to understand what this resistive impedance, what value this resistive impedance is, because depending on the values of resistance observed at the source, the transmitter, and at the receiver, the load, we can determine the reflection coefficients. So a reflection coefficient at either side is going to be gamma equals Z load or Z source, depending on which side you're talking about, minus Z naught over Z load plus Z naught. So we're going to have to calculate a reflection coefficient for the transmitter using RS and a reflection coefficient for the receiver using ZL. Now for most CMOS circuits, as we saw with pin pad design and pin interface design, the first thing we see on the chip is CMOS gates. CMOS gates are purely capacitive, which means that this Z load is going to be purely capacitive, and thus this load is purely capacitive, so that's purely C, and in terms of resistance, we see infinity resistance on this side. And so when we try to design transmitters and receivers so that we can minimize the amount of reflections we see, we have to consider the value of RS rather than the value of ZL, because ZL is going to be infinite. So the concern here is that the transmitter is trying to send a signal to the receiver, and we have to live with the fact that it's going to take a time of flight to get there. But if there's reflection at the receiver and reflection at the transmitter, then there's a possibility that the signal will take multiple times of flights to settle. And we have to understand what value of source potential, of source impedance, will help us avoid this. So we're going to look at three situations. So this is case 1, right? And in this case, we are using a value for ZL of infinity, because that's always going to be the case. The load is going to be purely capacitive, which makes it infinite in terms of resistance, but we are using a value for source resistance of Z0 over 3. And the results that we get here are going to be valid for any value of source resistance which is smaller than the characteristic impedance. So the results are going to be more or less the same, or are going to behave, in the same manner if ZS is less than Z0. So the first thing we do is calculate the reflection coefficient at the transmitter and at the receiver. So at the receiver, it's actually easier because it's going to be the same value for all cases, because ZL is equal to infinity. So at the load, at the receiver, the reflection coefficient is ZL minus Z naught over ZL plus Z naught. Because ZL is infinite, this is going to be equal to 1, regardless of the value of Z naught, and regardless of the value of RS, obviously. But for gamma Tx, we're going to calculate it as Z naught over 3 minus Z naught over Z naught over 3 plus Z naught. And this is going to give us a reflection coefficient of minus half. So it's going to give us a negative reflection coefficient. Now, as the source starts injecting the signal into the transmission line, it observes a voltage divider between the characteristic impedance of the transmission line and the resistance of the source. So at time equals 0, the voltage observed at the source is equal to Vs, which is the maximum value you are trying to inject, multiplied by the impedance of the line divided by the impedance of the line plus the impedance of the source. It's just the voltage divider. And so we only managed to inject 3/4 of the signal when we start, right? So, and you observe this here. Now, this is going to take a time of flight in order to reach the load. So the load observes zero voltage all the way up to 1 time of flight. But at the time of flight, what voltage does it observe? And at the time of flight, the load is going to observe a voltage which is equal to the voltage that is incident upon it, which is exactly this 3/4 of the V source. So we're just going to see V incident. But we're also going to see a reflection of V incident. So it's plus gamma Rx times V incident. And so it's going to be 1 plus gamma Rx times V incident. And so that's going to be 2 times 3 over 4 Vs, which means we're going to observe 1.5 Vs. And so at the load, you will see the signal overshooting and rising above Vs. What we want to see is we want to see the full value of Vs at the load. We don't want to see a higher value or a lower value. We just want to see a single value corresponding to the value we are trying to transmit. Now, this signal is going to reflect and go back to the transmitter, not all of it, not the 1.5 Vs, but the reflected component, gamma Rx V incident. So after another time of flight, at 2 time of flight, we see the value at the source updating. And so this is going to add, and so you're going to observe a value here of 1 plus gamma Tx into V incident, where V incident is this component. And so you will see that the source itself is starting to overshoot, again, above Vs. And it's going to reflect a component, which is this. Now, this component is going to reflect negative because we have a negative reflection coefficient at the transmitter. When it reaches the receiver after another time of flight, it's going to subtract from it. And so you will see this undershooting. And this will continue happening with the load reflecting back to the source and so on. And what's going to happen is that at the load, at the receiver, we are going to asymptotically, in an overshooting way, reach Vs. So what's the delay here? It's multiple times of flights. How many multiples depends on how close to Vs you want the received signal to be. Within 1%, within 5%, you have to define it, but it's obviously multiple times of flight. And that's why we are afraid of reflections in transmission lines. Now, this is another case where we have Z source higher than Z naught. In this specific case, it's equal to 3 Z naught. And obviously, ZL is equal to infinity. That's always the case. So in this case, the source is going to inject some of its V source into the impedance of the transmission line at time equals 0. And so V of 0 here is going to be Vs multiplied by Z naught, which is the impedance of the line. And again, we have a voltage divider, which gives you 0.25 Vs. So you see a very small component being injected into the transmission line. When this reaches the load after some time, you will not observe 0.25. You're going to observe more than 0.25. You're going to observe 1 plus gamma Rx V incident. And since V incident is 0.25 and gamma Rx is equal to 1, you're going to observe a 0.5 Vs at the receiver. Now, this component, gamma Rx V incident, is going to reflect back to the source, and it reaches the source here. And so the source is going to observe 1 plus gamma Tx V incident. And gamma Tx in this case is actually positive. We can calculate it as gamma Tx equals 3z0 minus z0 over 4z0, which is going to be half. And so again, it's going to reflect the component gamma Tx V incident, which goes to the load after another time of flight. And what you will observe here is that the load voltage is going to asymptotically approach the final value of Vs, and so is the source voltage, although the source voltage lags it by one time of flight. So how many times of flights do you have to accept as the total delay of the transmission line depends on how close to Vs you want to end up being. Now, the best thing you can do actually, and the last case we'll consider, is when Zs is equal to Z0, meaning that the source resistance is matched to the transmission line. ZL is equal to infinity as always. And in this case, gamma Rx is still equal to 1, but gamma Tx is equal to 0, meaning there's no reflection at the transmitter. And so what's going to happen is that the source is going to inject Vs multiplied by Z0 over Z0 plus Z0, which is half of Vs. This is going to travel to the receiver, and it will take one time of flight to get to the receiver. At the receiver, we're going to observe 1 plus gamma Rx times V incident, and V incident is Vs over 2, and gamma Rx is 1, so we're going to observe the entire Vs after one time of flight, which is the best thing that could happen to us. But we can't rest assured yet because we don't know what will happen when this component reflects back to the transmitter. So this component reflects back to the transmitter, and at that transmitter we have 1 plus gamma Tx into V incident plus the old value, which gives us a full Vs. And the transmitter is not going to reflect anything because it has a reflection coefficient of 0. And so then the voltage is going to stabilize at Vs at both the transmitter and the receiver, which means that the best thing you can do is match the source to the transmission line. In a lot of electromagnetic applications, you would actually also match the load to the transmission line. We don't do this here because we are actually dealing with CMOS circuits.